Variance, last time we talked about expected value. This is the variance of a discrete value. Variance, we mention it capital V of X. X mean it's variable. And also this variance mean population variance. So we denote this sigma squared. Okay, so you can denote it by capital Vx, V of X, or sigma squared. Same as what we did last time, expected value, it is simply population mean. So same here, this is population variance. Okay. This is how we find the variance. So you have to, I think, yes, you have to keep this in your mind. There are actually two ways to find this. We'll show, I will show you guys what are those two ways. This is one way. You have to get the sum of each xi minus mu. Mu mean expected value or population mean. Same thing, okay? Times squared times probability of that particular xi, okay? So summation. There is no I because we have mentioned under the summation note x in D. D is the all set of all possible values, okay? Which means simply you will be having xi's, x1, x2, x3, okay? So you have to get the summation. This is equals to expected value of x minus mu squared, okay? X minus mu squared expected value, okay? So I think you remember how to get the expected value. This means xi, let's say the middle one, xi minus mu squared times pxi, summation of xi minus mu squared times pxi, okay? If we use I notations, clear? So, or you can use expected value of xi minus mu squared, okay? You have to take each xi minus mu squared it, and at the end, take the expected value, okay? How to get the expected value? That part times it is probability of xi. Remember that? Okay. We will be having a few examples later. Or we can simplify the previous expression a little bit and get this expected value of x squared minus expected value of x squared. Everything is squared. Okay. So in general, we use this one and the previous expression as well. It doesn't matter which one you use. Based on your calculations, you can use either this one or previous one. Okay, clear? You don't need to prove these things. I don't expect it from you. But you have to remember this. Or anyway, if you have one short note or something, that's fine. Okay. Okay. Let's check this example. So x, we have xi's. We have 0, 1, 2, 3, 4, and 5, up to 5. Okay. The probabilities are given. PMF, which means each individual probabilities are given here. Okay. So let's check what they ask. Calculate the standard deviation. So what you have to do, I'm sorry to, I don't know why I cannot write it in these slides. Maybe okay. Sorry for that. So simply you have to apply your, simply you have to plug these values to your previous one of those previous expressions. Okay. So xi means 0, 1, 2, 3. X1, simple x1 mean, let's say simple x1 is 0. Simple x2 mean 1. Okay. So either way, here they have mentioned ex squared minus ex entire square. Okay. So you have to find this piece by piece. Okay. So first try to find ex squared. X squared, expected value of x squared. Okay. So how do you find that? X times, sorry, xi times pxi, right? That's how we find the expected value. Same here, but we have x squared instead of x. Instead of x, here we have x squared. So no matter what, simply plug the value. So x1 is 0 squared times its probability. Its probability is 0.05. Okay, see, first one probability is 0.05. Plus next one, x2, which is 1. 1 is squared times px1. Sorry, px2. Px2 mean probability of x2 means 0.1. See, I think, yeah. 1.5. Sorry, 0.15. Okay, it's not 1, it's a typo here. 1 is squared times 0.15. It should be the second one. I'm sorry, I cannot edit it here, but it is 0.15. Okay, I'll edit this and re-upload it into the same place. Okay, later today. Plus, likewise up to fifth one, x5, which means 5 squared times its probability 0.07. Okay, add those individual probabilities together, and you can find expected value of x squared. Okay, not the variance, x squared only. Next, you have another piece, expected value of x squared. Okay, so again, you have to do the same process, not for x squared, for x, expected value of x. Okay, so that you have to do 0 times 0.05 plus 1 times 0.15 plus likewise. Okay, but remember, each of them has a squared. So 0 times 0.05 squared plus. Okay, clear? Okay. Anyhow, they have given this value. So variance of x mean expected value of x squared minus expected value of x entire squared. Here, I think I missed something. Yes, I missed something. First one, see, I think the 8.03 is the answer for ex squared, but they haven't mentioned ex expected value of x squared. This is how we get expected value of x squared. You can calculate expected value of x. Okay, clear? Then take the square of everything at the end. Okay, not individual pieces, everything. So you can calculate expected value of x, just expected value of x, like 0 times 0.5 plus 1 times 0.15 plus up to 5 times 0.07. Okay, add them together. Then take the square. That's how it works. Okay, clear? I think I missed there. If I remember correct, I told you to get the individual squared. No. Okay, individual squared you have to take for ex squared. Okay, first x squared, then take the expected value of each of xi x squares. Okay, so please don't mess with these symbols, okay, or notations. Clear? Okay, I think yes, ex is given on the top. You can see expected value of x is given 2.5. So you can find the right hand side ex squared term by simply taking the square root of that. Okay, combine them and you can find the variance. Once you need to find the standard deviation, you have to take the square root. Okay, you have to take the square root. That's it. Okay, since you have calculators, it is easy. Normally we keep it like 3 or 4 decimal places. That's fine. Okay. Right? Any questions? Just plug the values into the expression, one of those expressions. I think this is the easiest one because I use this formula for this formula to find the variance because this is easy. Expected value of x mean, simply mu, your population mean. If you know the population mean, you can find the last term. Okay, like that. I think we had one slide to show you guys how to find those values one by one, like using a table. I don't think we need it because you are using calculators. We don't need to do it by hand. Okay. Standard deviation. So there are examples here. If let me check. Yes, there are two examples. Yes, there are two examples. Just mention what is the scenarios. Suppose you are tossing a fair coin twice. Flip the coin twice. X is the number of tails in two tosses. So number of tail can be 0, 1, or 2, right? So I think you saw the picture for that few slides back. Another example. Randomly selected vehicle passes its emission test. We say it is a success denoted by x equal 1. Or it is failed, which means x equals 0. Success or failure. Okay. So there are two values. We call it Bernoulli random variable since it has two values. Yes, so it's PMF. You saw this example previous slides. P1 is simple probability of 1. We denote, let's say, simple P, and P0, 1 minus P1, which means 1 minus simple P. Okay. Standard deviation. Yeah. For these cases, you can find the variance as well. I think you can find the variance for second one. Please check it. Okay, it is the easiest case. You can find the variance. Okay, I'm not going to find the variance because in next chapter, not in next chapter, next section, we have to find those expected value and variance as well. Okay. Okay, variance. Same as if we have a constant, like for the expected value, we had something. Variance of ax plus constant. So that variable x has a constant. Addition to that variable. So variance of ax is ax plus b. You can simply, okay, assign the variance for each of terms, each of them, like variance of ax plus variance of b. A and b are constant terms. Okay, clear? So you can assign the variable, you can assign the variance to each of them, which means variance of ax plus variance of b. Okay, so here's the deal. Variance of any constant is 0. Okay, variance of any constant value 0. So simply variance of b is 0. Okay, so you have only variance of ax. Okay, any constant join with the variable, you can take that particular constant out from the variance. Once you take the constant out from the variance, it get squared. Okay, that constant get squared. So once you take out the simple a from the variance, it get squared. So you at the end you have a squared times variance of x. Clear? That's the variance deal. That's the variance how it behaves. Okay, clear? Any constant with the variance? 0. Okay. What's the next one? Yes, standard deviation. So simply you can take the square root of the variance and you can get the standard deviation. We have mentioned here absolute value because we are considering only positive values. Okay. Clear? A variance equals to sigma squared, or you can denote it sigma x squared, same. So, okay. So, second one, check the second line. Where square root of variance of ax plus b, which is equals to absolute value of a times sigma x. Okay. Same thing, because variance of a constant is 0, sigma ax is same answer. Okay. So constant doesn't matter with the variance. Clear? Okay. So that's why second line and last answer in the second line and the third line, they are equal. Okay. Only difference is they have a, sorry, the first guy, they it has a constant value, b, simple b. Okay. Clear? Okay. Okay. Very important section, binomial distribution. This part, in this section, we have to discuss binomial distribution as well as Poisson distribution. Very important to discrete variable distributions. Okay. Binomial, simply binomial distribution start from, if you do you remember the Bernoulli random variable? So binomial is a collection of Bernoulli random variables. Okay. So each of the binomial variables is consist of Bernoulli variables. Okay. So each of them have two possible outcomes. Like if you are flipping a coin 10 times, consider the series of those 10 items. So each of them has only two occurrences, right? Either head or tail. So all 10 we can consider like a binomial distribution. Okay, clear? That's the easiest example. Binomial setting. N, simple N, these letters, simple N, those are a little bit general terms. Simple N mean trials. Remember that these trials, simple N trials, they are identical, which means they are independent to each other. Okay, trial number 2, it doesn't affect to trial number 3 or trial number 2. So trial number 1, something like that. Okay, they are identical, which means they are independent trials. Okay, that's a ground rule for the binomial distribution. Okay. 50 example, 15 tosses of coin. If you flip the coin 15 times, they are independent trials. Each of them are independent. 10 CDs chosen from a warehouse. CD can be defective or non-defective, something like that. Okay, they are independent. So they are mutually exclusive outcomes. Outcomes are mutually exclusive, either success or failure. Most of the time we use these two words because we have either success or failure, because outcomes are only two. So we call it success or failure. Success or failure based on how you define your question or how you define your problem. Okay. For an example, if I say, okay, I'm flipping a coin. I want to see how many heads do I have after I flip n times. I need to check how many flips, how many heads I get. Okay. So number of heads is my success. Clear? Okay. Another way. I'm going to flip the coin again, but this time I need to check how many tails do I have. So right now, my success is number of tails. Clear? So success and failure based on your definition or based on your how you define the problem. Clear? Okay. Trials are independent. Okay, they have nothing to do with the others. Probability of each occurrence, I mean probability of each outcomes, they are constant. It doesn't change during the experiment time. Let's say having a head. Okay, having a head, probability of having a head is 0.4. Okay, having a head, the probability of having a head is 0.4. Then it doesn't change for any any flips, it's remain constant. So having ahead a 0.4 for flip number 1, flip number 2, or flip number n. Clear? It doesn't change. That's really important. Okay. This thing we call in advanced statistics or advanced probability, we call this ergodic theorem, ergodic case. Okay, so probability doesn't change. Okay, let's see how we define the binomial distribution. N mean number of observations. Simple P denotes the success probability. Okay, simple P denotes the success probability. Clear? So again, random variable X counts the number of success. Binomial distribution, it's random variable capital X. It considers the number of successes. Okay. So you can imagine that X values can be 0, 1, 2, 3, 4, because X is again a discrete random variable. Okay. Okay. 0 is possible, 1, 2, 3 up to n. It has a limit. Okay. It has a limit at the end. So simple n is the total number of observations. Clear? Okay. Let me go to the next slide. Okay. Yeah, X can be integer between 0 and 1, 0 and n. Okay. Including 0 as well. Okay. It is the example here. Just check this example because I think based on this example, there are few another examples in later slides. 3 independent opportunities. We have 3 independent opportunities to check whether the CD, CD is defective or not. I think it is CDs. Okay, no. For error in assembling the component, any component. Okay, we have 3 chances to check that. So each opportunity, probability of having a defect is 0.1. It's a constant for trial number 1, trial number 2, or trial number 3. Clear? Okay. Assumptions, normally we denote this like assumptions. Simple n, number of observations. Here n is 3. Okay, in this case, your example, number of observations are 3. Either error occurs or not. Okay, only 2 possible outcomes each time. Yes, error, assume the chance of an error, same for each trial. Okay, which means the probability of having an error is 0.1 for each time. Still we don't have the distribution. Okay. If we need to check the number of defectives, that's our success. Okay, so we are considering number of defective items, 0, 1, 2, 3. According to this example, maximum can be 3. Okay, so success is number of defectives. Okay, exactly 1 defective, more than 1 defective. Okay, okay, this is the binomial coefficient. First of all, before you go to the before I show you the binomial distribution, this piece we call binomial coefficients. So they are dealing with factorials. You can write it within brackets, simple n, and down below k. Simple n means number of observations. Okay, total number of outcomes or total number of trials. Okay, I would say total number of observations. Simple n. K is the number of successes you have. Okay, so definitely K less than or equal simple n. K cannot exceed the limit of n. Okay, clear? So you can expand that like factorial n divided by factorial k times factorial their difference n minus k. Okay, clear? I think you have seen this factorial, right? Okay, so if you consider the previous example, if I consider just one uh, just one success or just one defective item, total number of outcome is 3 or total number of observations are 3. I have 3 trials, independent trials, and successes just one. So you can simply plug the values into this binomial coefficient and find the value. Okay, how many times I can get just one defective item. These are like combinations. I didn't do this in chapter 2.3. It's optional. You don't have to worry about it. Okay, just based on uh, yes, based on that. Okay, how you choose to have many possible outcomes. Okay, okay. Here n minus k can be 0. It doesn't matter. 0 factorial is 1. You already know that, right? It based on prime factors. Okay, right? Clear? So don't worry about 0. 0 factorial is 1. It's defined that definition based on prime factors. Okay, like since I cannot write it, I cannot show you here. Anyway, this is the I'll finish it from here. I mean this one. This is the binomial distribution, or simply you call binomial probability mass function, or you can say binomial distribution. Okay, we can denote binomial distribution like capital B or simple B or BIN, something like that. Okay, doesn't matter. But inside after that, let's say, yeah, simple B. Within bracket, you have to mention what is the variable, what is the number of possible outcomes, and what is the success probability. Those 3 variables should be inside the brackets. Okay, so you can say capital BIN, within bracket my variable is simple x, semicolon n, simple n mean all possible trials or number of trials, comma, simple p is the success probability. Okay, or later you can simply cut off this random variable simple x. Okay, and you can write capital B within bracket n comma p. That's enough. Okay, so this mention point probabilities. This mention probability of capital X equal simple x. Your binomial coefficient in front n x, and probability of simple p means success probability. Simple p to the power x times 1 minus p to the power n minus x. So you have to remember this one. P and 1 minus p, you know, they have like verse wise process, right? Simple p, 1 minus p mean 1 minus the negation. Okay,